Hello, everyone, and welcome to the webinar. This is the first in a series of webinars that we'll be having now. And today's webinar, as you can all see, we'll be talking about the integration, SolidCAM integration with robot software. This webinar will be given by Harold Schumacher, who has been working with this for quite a while already, and who is our expert now in this particular field. Now, before we start the webinar, I'd just like to mention to everybody and remind everybody that we have the SolidCAM World 2019 coming up in Orlando on May 15th. So if you have not registered yet, please register it as soon as possible so we can make sure we have enough room for everybody. There is a lot that we will be doing there. Orlando in itself, there's always a lot to do in Orlando. But we have a very full menu as far as venues that we'll be doing at the SolidCAM World Conference. So please, everyone, your invitations have been sent to you. Please register for the event as soon as possible. We also have the agenda that can be seen over there, and hope to see you all there as well. Okay, so now let's get started with the webinar. I will make Harold the presenter, and Harold, you can unmute yourself, show your screen, and go ahead.
Yes.
Okay, we see
you see my screen?
Yes, we do. Go ahead.
Okay. Hello, good morning, and welcome to the webinar also from my side. Today, as Sidney told you, we are talking about our integration to robots by the Eureka interface. Okay, today's topics are basics you should know before you start milling with a robot. I will introduce you Eureka, the robot solution from Roboris. We will show the interface to Eureka, and we're preparing a CAM project for a robot cell, and we are talking about specific situation with the robot kinematics you probably need. So what you should know before you start milling with a robot. You have maybe toolpaths from where you get your toolpaths. So you can get it by teaching and so on. I will come to that point later. Be thinking about what data the robot needs, if there are any limitations, what data you can generate with SolidCAM, and finally, what do you need to generate the G-code, what will operate the robot. Toolpaths, from where you get it. You can teaching all the movements to the robot by hand, but this will be not common for milling operations. But you can also teaching virtual toolpaths in a robot simulation software. What you see in the middle, in the picture, you see that case where you import data to your simulation software. You select elements and you apply vector for the tool and moving along. Or you have a specific robot CAD/CAM system, and then you can do that there everything. Or what I'm going to show today is generating the toolpath with SolidCAM and use it on the robot. We have to be sure that you know that there are some limitations in the accuracy. It depends on the number of joints and the size of the robot model and the position where the robot operates, that we have a limitation in accuracy. If you see on the left side, you see a robot which looks more solid, and the place where it operates is more closer to the base, and the angles of the robot are more closer. And on the right hand, you see the robot has to go more far away from its base, and you can imagine it's more thin, that if you cut the same part with the same cutting conditions, that we expect that the robot on the right hand has more accuracy problems. It's in the nature of the robot that tolerance in each position is relatively inaccurate. If we know that that there is a problem in accuracy, it's clear that we cannot cut very hard material and long parts with a wide range where the robot arm has to go to. So as less strength the work material has, the better the cutting result will be obtained. What you should know is that a standard robot used for milling operation needs to be calibrated and prepared for offline programming. If prepared well, then a G-code for the robot has the same needs as a standard CNC machine: home position, setup information, tool changes, etc. We need to understand that the linear arc movements, they have to be given in a special format. So the target of this linear movement is given as a position and orientation of the tool coordinate system, what you see here on the head of the robot, with respect to another coordinate system, what can be here the base or the world. But most important to understand and to know is that robots don't have a look-ahead function related the G-codes to avoid collisions. Robots moving in the shortest distance mode from point to point without taking care if the movement is possible or not. So when we see these two pictures, we see the same position in the G-code, what is sent to the robot simulation software. The robot moves on the left side from its last position in the shortest distance to that point without taking care that there is a table, that there is a collision or anything else. And on the right hand, you see, is one of the possible combinations it can go, but it is not the shortest movement to that point. So what data you can generate with SolidCAM? With SolidCAM, we can generate the complete setup information for the robot. We have fixture stock target definition, home positions, all needed toolpath information, program infos like a position and tool vector, rapid line, arc movements, tool changes, etc. So far, maybe you think why we not to use the SolidCAM G-code directly if we have tool vectors, if we have everything. The main point is that the robot moves directly from the last position to its next position, and that is the main problem we see. And if we are looking now a little bit closer to that subject related to the G-code, the format of SolidCAM does not match directly to the robot. SolidCAM's output is based on a maximum 5 degrees of freedom, while a robot has 6 or more axes, with an external axis, for example. And this additional axis can be fundamental in complex machining. Another limitation what we should talk about is that almost all robot controllers don't have a big memory. So far, that forces us, if we have long 3-axis or 5-axis G-codes, they need to be splitted. There are options for DNC remote control, but it's only with a lot of effort and workarounds possible. So finally, what do you need to generate a G-code which operates the robot? You need a virtual environment. We are talking about that later. It's the robot solution from Roboris. You need the toolpath, what's the SolidCAM output in APT format. And you need finally the G-code, what operates the robot. And this is generated by the robot solution from Roboris. Basically, Eureka is an NC verification and simulation solution from Roboris in Italy. They have NC verification for milling, mill turn, and robotics. And the robotic module is an extra module because here this module generates the real G-code which operates the robot. So they have options for sculpting, painting, thermal spraying, deburring, cutting, welding, and so on. There are a lot of conditions what they can support, and it's this is a topic for a specific webinar. Then maybe Roboris can give. Some basic slides about the product itself. This is the logo of the software. It's from Italy. Yeah, the robot module is for milling and sculpting, transform the robot into a machining center, what we are talking about today. They have options to analyze and compare results, monitor axis and speed, and estimate machining time, compare machining stock with the design model, all this stuff that software has. And but I will not talk about those complex topics. I'm concentrating on the main problem I showed in the beginning, that there is a fix and optimize solutions, detecting singularities or limits, and how to fix them and how easy to use is that handling. There is some of the brands, they are supported. I got yesterday some more supported robots, so this is not the latest models they support. And starting to talk about the SolidCAM interface to Eureka. Basically, it's the G-code simulator option in SolidCAM, and this interface becomes visible if Eureka is installed and the interface is configured well. And for you as a reseller, it's open, and for end users, it's a software option. The interface has some options for specific tasks. The main option is to export all the data and run the simulation. And for other tasks, we add, let's say, some updates that we only add exported data, or we generate a separate tool table if there are some tool changes, or if only we update a NC program and for some special cases. So preparing a CAM project for the robot cell is the same way of defining your CAM project for a standard milling machine. You define your stock target fixtures, and the right-hand picture shows you that. Sorry for that screen. Yeah, The right-hand picture shows you that there is the base of the robot and the block where we mount the parrot, and the picture that we see the relation how that project will be sent to the cell. Here is a short step, also a video how to export and how to bring a project to Eureka. Is simply click the operation, export and run simulation, and it's ready to play. So far here on the right hand, left hand, you see the G code we or the apt code we sent, and you simply start playing the simulation. Here is a stop and zoom closer. We see the movements on the robot with its kinematic, and we see that on the left hand all the lines are blue, and in this case we are ready to generate the G code, and we see for the robot, and we see on the in the center window from here that this is the real code which is working and operating the robot, and this is the code we provide from SolidCAM to tell the robot where to move. So I'm coming now to the live demo for the problems you see. I'm going to show how to check the collisions of robot axes and how to fix them. We will see in the simulation that we have typical singularity problems with the robot and how to fix them. And the most important point is to check the first movement to approach to the operation, and how you approach, in which relation of the kinematic of the axis of the joints of the robot you approach to the point, and then how easy it is then finally to get you ready to use G code to operate the robot. So I'm switching to SolidCAM. This is the same project we saw already here with some more operations, and I want to show you shortly the setup again, or the machine simulation. We can talk about also in the machine simulation about it. Machine simulation. Why a machine simulation is added to this project? Because we want to see, or I want to see, it was my focus, I want to see on my parrot that I have a collision-free operation, and I want to control my tool, I want to control my holder, and I want to control a part of my spindle, let's say, in this area. This is for me the most critical operation part of the machine here in the moment. So far, if that is for me in my machine simulation, okay, I can continue programming my parrot and so on, and make my verification, and I see that I have the same behavior as I'm doing it with a standard CNC machine. Yeah. So far, nothing to know, especially that there is a robot behind now. Okay, that was the reason why it's added, and it makes also sense to imagine where the robot has its base and where your part is located. That is our setup information is well supported, so you can shift your parrot somewhere on the table, and you can generate your G code related to the position which you add or modify in your setup. Coming now to the transfer to Eureka. So far we are here. Shortly a little bit to the user interface. We have on here, we have the kinematic tree of the robot. We see here all the joints of the robot and tool frame, spindle, and so on. We have here the program window, what we can show, play buttons and so on, and some other options, what we see during the presentation. Okay, the project is ready to play. What I will do, I simply click to play and check what happened. Yeah, we see that in the moment everything is okay. We can so we support 5-axis toolpaths, 2D toolpaths. And as long as everything works fine, we don't have, okay. So we see that there we have now the first case of a collision. We see that the toolpath here operates well, everything is blue until that point. Here's the collision happen, and here we see that the tool needs to go more down and it will collide with the robot arm. So far, what to do now? It's very easy with Eureka. We have several options. I want to show you some. I have the option to go a step back in the program, click on the right hand, and have a Z rotation where I can rotate the Z axis. Let's see what happened here. I can move the robot along with its axis around the point. The tool vector stays in place, and I see here is the critical area. That is here is the maybe a collision again, and I move it around to see. Okay, let's go to this point and see what's going on. Yeah. So far, this will be updated and confirmed, and you see the line is changed in the program. So far I can go back and see what happened. I'll make the simulation speed slower. And click the simulation. You see it's coming to the point, the robot rotates around the point and continue to work. You may think that this is not good, that the tool rotates on the point, rotates around the axis. There is a tolerance. Maybe you will get a gap or a gouging that there is now different cutting forces and so on. We can solve this also in a different way. So far, when I stop the simulation, I can go back to the first place of the operation. And that is what I said in the beginning. The robot moves from its last position and its last relation of the axis to the next point in the shortest distance mode in all the directions. So far, if we are going to change the initial position of the operation, the robot has a completely different behavior, because the first operation tells me a different point. So far I click, is this the operation? Let me see, let's come to a profile, is that not that? To find this approach point. We are already here. This was our approach. We should come now. Here we are. We have here the approach. Here we see this is the initialization of the position, and we can use the option approach to approach. Okay, we approach, and here we have, you see the axis and the joints of the robot, and here we have the same option. We are outside the part. We can get the robot into a good position. And we now replace this movement. We replace this movement with a movement called move joints. So that means we change the format, the line where we have x, y, z in our vector. We change that and replace it with the position of the axis of the robot, and not of that we change the coordinate on the point. So far, if we now play that movement, a robot has to change its position, start with the same point, and we see a completely different orientation and different behavior moving to the point. So far, here we have the next collision. So far, it was not so good idea to move it so close around. So far, I have to go back and modify again my start point. Same way, I have to fix this approach, and here I can do it in a different way. I have also options with a jog. I have here an address of axis where I can say, okay, I rotate my axis by hand, or I can use some buttons here and say, okay, here I want to move around J1. I move around this axis, and now I want to go a little bit more to the side and a little bit up, down, up. And this should now my new approach point. And to find again the place where I did the first changes. And check it again. Another problem. So far, this is what what is the try what we have to do to fix those movements with the robot. Here we say, okay, let's make it short, move it to this way, confirm, and continue. Okay, looks good now. Everything is blue. So when in Eureka the toolpath was valid, we see here that everything is blue. There are no different colors. So we are ready to generate now the whole G-code for the program. No, we are not able to do it. Let's say do a restart to see to get aware of this errors we have. First, to see that we have everything in green. It's another complete test of all operations. Remember, we said the robot moves from last position to next position, and if we modify something, we change the whole relation of the robot joints, and that can maybe affect some other operations. So now everything is okay. And here is then the point where you generate your post-processor, your G-code with the post-processor for this specific robot. Here is the code. Okay, so far that is let's say the basics, what you need, and I want to show you also some options we support here. If we are going to start the robot, we see that we are in the initial position. Let's say this is good that no axis is on 0, that the robot has any orientation, that he knows how to move to the next position. So if there is maybe a singularity where it doesn't know where to go, it will give you an error. So far, it's sometimes good to have some position that the robot start with. But let's look on the points. We have here a tool change. And if you have a tool change on a robot, some robots they have a tool change, some robots not. We see that the tool is somewhere changed here in the air and then move to the part. If we are going to SolidCAM, we have also supported to use machine control operation. So if I'm using a machine control operation, move to tool change position and start, I define some movements where I'm want to be able to control the first movement. Remember, that is the key issue, to control the movement from the position, from any position to the start point of the operation. So far now, we know that the Eureka is running in the is already running, and we only need to update on the same robot only the NC program. So far we can go back and stop that this latest simulation, load a new program. And looking now on the situation of the tool change, what happened. From the initial position, the robot goes down, move along, and maybe that looks safe or looks not safe. That is up to the operator if they are want to keep this movement as it is, and then move to the start position and do the operation. So far, the same style of changing the approach is we can do here with our movement. So we see here that that was our first movement of the robot coming to this position, and this is the next position. So far, I already add a movement what I can play with and say, here I want to have an approach. If with this approach I can rotate my robot again and see, okay, here is maybe it's not so good, yeah. Or let's see, maybe that movement looks okay, and replace it with an move J. So far, we see what happened. It's changing the head, moving to the position, and do a collision. that is what that is what we have to really take care on. This approach to the point, move along, and maybe you're not thinking you cannot see it in the beginning that this might affect in a collision so far. You have to go back and change that point to bring it back to a good one. Yeah. Okay, here we said that is not so good. And now I need to find a better place where to go. And I try another position. No, this is not good. Let's try that. Okay, this looks better. Tool changed. And start position. No, this is not good. Okay, we have to go back. This is the last movement to the point. Now we go here. This is the movement to the start position. And I say, okay, take an approach and leave it like that, for example. Yeah, this is a try and error. Let's say I can't define these axis values by hand. You have to move the slider, find a good place, replace this as with the move joints, and inspect how the robot moves to its position. And if it's on the pivot, okay, we try to continue and see. Here we see that there is an axis limits. Let's stop. Where is the axis limits? What is the problem here? This is maybe an old error. Let's see. We make now a restart. We see everything is green. And program is done. And you can generate now your G-code for the robot. Okay, I have some other examples to show that. Some more options. It's a robot which is using an external axis. So for us, for SolidCAM, it will be a 6-axis machine. Yeah. So far, we have here, show you the machine simulation. We have here the head as a 2-axis a kinematic mode, and we have the table, which is then the 6-axis. And I'm going to show this how to use this in with Roboris, with Eureka. So far, we have here prepared some operations where I have here a submachine supporting the table rotation, and I'm sending only these jobs to Eureka. And we see new robot cell with the rotation. So you see that the robot starts to cut. Never mind about the operation itself. It's if the toolpath would look in the machining like it should be. It's only showing you how the toolpath passed to this Eureka, and we see how the external axis is operating. Yeah. Let's go faster. And you see with in some cases the initial position of the robot and your operations and your start points of the operations matching with the robot, but here you need to verify it with the kinematic of the robot, and you be sure now if you get collision-free simulation, you will get also collision-free machining. Coming back to, we change now the submachine where we have 5-axis settings, where we have kinematic axis X, Y, Z, A, B, and some operations. We are calculating always the updated stock that we see the real situation on the simulation. So far, same case, same play, and start the simulation. And we run into a problem. You see here that the robot has detected the singularity. Now it cannot move ahead because of this case of its kinematic. It's so not possible for him to decide where to go, and we need to help him to get his orientation. The same thing. I go inside the program and see, okay, this was during the operation, and now I change only with the Z rotation this position, go around and say, okay, this is for me a good case, update my simulation and continue. We see what happened. Okay, moving along, and it's okay. Then we have the next problem somehow. Where to go? Okay, the robot wants to go to the side and wants to mill here, and here we are out of limit, and we should give him a different approach. So far we go back in this operation. Oops. And we change here the case. So I prefer here to use the approach to see here the cases where it looks good. Okay, and if it's in the moment for me to close on this point, I can also easily then replace as a joint, easily change this position by now modifying it with the axis, where I say, okay, move with the Z-axis more far away from the point, go back to this, go back. I need to go back. And I need to how to get it back now. Replace this. What options I have? Let's see I cannot change the approach again. Let's say set next line. And move there. And oh, I don't know why I cannot change now the position again to replace this line again. Maybe I can delete it. I can get a refresh of the program. But anyway, let's see if we do it good here or not. This may be the problem of the previous operation. We see here, first we fix this also. This case, we go back into operation. So it's now all the time I am repeating myself, finding a good approach point with the robot. Here, the approach is available, and I move the slider to see, okay, this is a good approach point. Okay. And replace. Okay, I can also insert that line to keep my line before, or I can say, let's replace it with a move joint. Okay, it looks that it can operate. What we have here, material, movement, okay, well, where the robot has to go. Okay. Wants to move to the side. And we have to, again, to fix this issue. We are here on the left side. I need to go to this point, and this point is too close down, and should find a better way to move to this point. I go to the joints, to the jog, and there are also options to move with a virtual box. You are able to touch the box on the points, and you see in the background. Let's move it to the side. You can rotate the robot completely with, or move it into the plane. And now I move it a little bit more up. And I want to avoid this axis. And this looks maybe better as an approach point. And I want to replace this with this movement. Let's see what happened. This is the problem. The robot needs to rotate here the head and move along. So far, it's better to be here on the place and add here movement to say move along, more far away. It's maybe depend on your retract area in your operations that you not retract enough. And we can here insert, I think a go-to, that it's go to this point. Play. Okay. What happened? It maybe not. It was not so good movement here. Okay. And maybe a move joint would be better in this case. So we insert that line, so we can simply delete it. We go back to the point. find the position. This is point here. This is the point here. So looks. What is the point here? Ah, yeah. Okay. It's not possible. This movement, and we retract again. We do try it again. Try it again. But we are already here. This is the case where I am. And then replace this movement with the move J. It's moving up, now changing the okay. Maybe this is a limitation of the axis of some hydraulic wires and so on, yeah, but this maybe can really necessarily movement that the robot knows to orientate here in a different position. Here we have a singularity during the toolpath, and again here I can do a small Z rotation, give him a link to say, okay, let's go like that, and continue. It seems that this position is not so good, yeah, because you see everything is straight, and there is all the time running into a singularity. We go back to our operation, and we are here, and we can think about what we can do. Let's say we go to the jog, we go a little bit more to the side, and give him a little bit different angle. It's okay, replace this movement where it is as move joints, and see now what happened. Okay, we have here axis out of limit, so now we have a different other problem. So far, I repeat all the time now that the same actions to get a good toolpath to run a complete program. So far, that is what I want to show, that you need this environment to fix those issues. You make your collision checking with your environment, and you generate finally your G code with with Eureka. Coming back to the presentation, talking about the configuration of the interface. Interface is very easy to configure, because the software already has all the functionality inside. With after your installation, you don't need to install extra software from SolidCAM side. The interface is there. You need to install Eureka. You have to set the path to the X of Eureka, and you create your machines directory where you save your your different robots as subfolders. And then in your CAM part setting, you select your robot, what you want to see in the projects or in the simulation, and then you're ready to play. Before we start about answering questions, I got already some questions through the time, and yeah, this I want to share with you. So we are the developer of the interface. That means we take care on the export data, on the format of the data. That's the project is running. So we have the control about that our data operating well with Eureka. if there is any troubles with the interface, so for users, please contact first your local SolidCAM reseller, and resellers, please talk to SolidCAM Ltd. In the beginning, I talked about the robot environment. Who prepares the robot to make it happen that you can mill with it? Usually it's done by the reseller of the robot, or they call it a robot integrator. So far, you can buy a robot from KUKA, and the robot comes and nothing is working. And then there are some sub companies. Yeah, they are specialists in make the installation of the robot, set up the robot, and do that kind of integration, that it's the calibration and so on. Yeah, who will do the installation and configuration of Eureka and the test of the post-processor for a specific robot? Roboris prefers that a SolidCAM reseller does the installation, if a SolidCAM reseller wants also to be a reseller of Eureka. In other cases, you are supported directly by Roboris. They have some companies here. One, the headquarters located in Italy, and they have a company here in Germany, and there is also a Roboris USA, and then you should find your best contact to order the software. So what the SolidCAM sale will include, or what should it include? It's the sale will come with the post-processor, what we generating the G-code with, sending it to Eureka, and the option to open the interface. Then last point is, if you are going to sell the option for the G-code simulator, this is important to express in your offers. Maybe the users, they're thinking, I have an option for a G-code simulator, and they push the button and nothing is working. We have such cases in the past so far. This is why I'm talking about. So you need to make it clear that the delivering of the interface contains only the option to export the data from SolidCAM to a dedicated folder, which will be then the folder that the software Eureka will take the data and run it. But it will not include the robot simulation software. This is an extra separate license. What I had talked before, you have to order the software from Roboris, and then do the installation. And after you set up the license bit, you can start generating G-codes for your robots. So far, Sydney, I am done.
Okay, Harold.
Is there any questions?
Yeah, there's just one question, and I don't think we can do more than that anyway because we're running late. There's one question where just asking, maybe you did answer it already. Are there any solutions such as competitors that avoid the trial and error process for positions to avoid collisions?
In the solution from Roboris, there is no automatically avoidance of a collision. Yeah, I don't know if I think other specific robotic CAM systems, something like that, they have such the case. But here in the moment, there is no automatic avoidance, and you have to manually fix it.
Okay, Harold, thank you very, very much for the webinar. There's a lot, obviously, that you've shown here, and there's a lot that you can do with robotics that I didn't even know existed. It was very informative. And one more thing I'd like to also mention to everyone. Next week, we will also be having a webinar on what's new in SolidCAM 2019 SP1. So you'll be getting the invitation to that on that as well. And one more reminder is that please everyone sign up for the SolidCAM World in Orlando. There's a full venue. There's a lot that we'll be doing over there. So sign up as soon as you can. Thank you very much, everyone. This has been recorded and will be available to everyone later on. Take care, everyone. Have a great weekend.